All right, let's take a look at the concept of an equilibrium constant expression. So hopefully my comparison earlier about people going on and off the court was helpful for a chemical equilibrium. And maybe I can extend that comparison and say for each reaction, the amount of products and reactants that you end up with is going to always reach the same state, the same equilibrium state. Kind of like for each different sport, the amount of people on the court or on the field for that particular sport is going to be constant. But it could be different for different sports. This can be different for different reactions, but for each reaction, you're always going to reach the same type of balanced equilibrium state. So we're going to learn how to write equilibrium constant expressions. This is the general setup, that we have the concentration of products in the numerator, the concentrations of reactants in the denominator. We have this shorthand here. If you write a chemical formula in some brackets, then that means the concentration of that substance, so that we don't have to keep writing concentration a lot of times all over the place. It's a long word. So one thing to remember that might not be obvious at first is that the only products and reactants that we're going to concern ourselves with are gases and substances that are in aqueous solution. So if we see something that is G, or if we see something that is AQ, that substance has to be in the equilibrium constant expressions. If something is S or L, solid or liquid, then the concentration of that substance doesn't really change very much. You can't say, oh, well, how is the concentration of this piece of solid zinc changing? The amount can change, but the concentration is not going to change. And so by convention, we count those concentrations as 1, and so you can leave it out. And then any coefficients that are in front of the chemical formula of a gas or aqueous solution substance will become an exponent to the concentration. All right, so this really isn't too bad. It probably is easier to do than it is to explain. All right, so writing this equilibrium constant expression, we have to put the concentrations of the products over the concentrations of the reactants. So for our products, what we have in this reaction is HI gas and HI gas. So we have 2 molecules of hydrogen iodide gas as our products. And so our products are the concentration of HI times the concentration of HI, because we have 2 of them. And then the reactants, we have 1 hydrogen and 1 iodine. And then instead of writing this twice, what we do is we just take the coefficient that we had, the 2, and write it as an exponent, just to show that we had to multiply it twice. And then these ones, we only have 1, and if the exponent of something is 1, then you don't have to write it. So we just write them like this. And all of these are gases, which is why we used all of them. Let's try a couple from this problem. These are all gases, so we are not going to worry about leaving out solids or liquids or making them equal to 1. So we're going to have the concentration of the products over the concentration of the reactants. So let's write it like this. Okay, so the concentration of products over the concentration of the reactants. The products are NO2, and there's 2 of them, so we're going to, instead of writing it twice, just write it as NO2 squared. And then we also have NO twice, so we're going to put that 2 as an exponent. And then the oxygen we only have once, so we'll just write that without an exponent because the exponent is 1. So this would be our equilibrium constant expression for this reaction. This one also has all of the substances being gases, so we're going to use all of them. Our products our carbon disulfide, and 4 hydrogens. So we have 4 of them. We're going to make that coefficient the exponent 4. And then we have methane, CH4, and then we have hydrogen sulfide, and that we have 2 of. So we're going to put an exponent 2 there. For this one over here, we have both of them being gas. So the products are NO2 with an exponent of 2. The reactants is N2O4 with an exponent of 1 that we don't have to write. For this one, we have aqueous, which is another one that we include, so we're going to be including all of this. We'll have the products on top, and there's only 1 of that, so I won't write an exponent here. And then the reactants, we have the lead-2 ion, and we have the hydroxide ion. There's 3 of the hydroxide ions, so we'll put the exponent 3 here. All right, we have a couple more examples to try, but this time, not everything is a gas or aqueous. We have some liquid mercury and we have some solid mercury 2 oxide. And so these concentrations are going to be set to 1 by convention. So our products go in the numerator. Concentration of mercury liquid is set to 1. You can square it if you want, it'll still be 1. And then you have the concentration of oxygen, and the exponent would not be written. And then you have solid mercury 2 oxide, which also has a concentration set to 1, and that would be squared. But 1 squared is 1, 1 squared is also 1. So you can simplify this and just have this be the concentration of oxygen. The concentration of oxygen over 1 is just the concentration of oxygen. For this one, the only gas or aqueous substance here is the chlorine. So our product, PCl3, the concentration would be set to 1, and then you could square it. For the reactant, the solid P4 would be set to 1, and then the concentration of chlorine gas would be raised to the 6th power because of that coefficient. So this is probably the simplest way we can write that equilibrium constant expression. For this one, we have a few more that are gas. It's just that not all of them are going to be used. We have hydrogen gas, carbon monoxide gas, and then we have water vapor, also just a 1 coefficient. And then the concentration of solid carbon is just going to be set to 1. So we don't really have to write that. Most places you won't find it written. You would only find the equilibrium constant expression written like this. So we have a couple of special cases for equilibrium constant expressions. We have the equilibrium of dissolving something. So when something is dissolving, if it doesn't dissolve completely and you have some solid left over at the bottom of the test tube, then that solid is actually dissolving, but it's dissolving at the same rate that the other dissolved substance is precipitating out. So since it's dissolving and undissolving at the same rate, it's in a constant state, and we can figure out what the solubility of that compound is. So for these reactions, since they represent dissolving, instead of writing KEQ, we call this the solubility product constant. And so that is the concentration of the barium ion times the concentration of the sulfate ion over the concentration of this barium sulfate solid, since it's a solid, would be set to 1. And so it would be written like this. So for this one, we have lead-2 ion as a product and also chloride ion. The thing about the chloride ion is that it needs an exponent of 2 because there are 2. And then the solid lead chloride would be equal to 1. And so the solubility product constant for lead chloride would be the concentration of lead 2 ion times the concentration of chloride ion squared. Another type of equilibrium constant that's kind of specialized would be that of a weak acid or weak base, because we looked at before how weak acids like acetic acid are weak electrolytes. Not all of it separates into ions when you dissolve it. Most of it stays together as a molecule. The thing about that is that it's a reversible process. So some of the molecules are falling apart into ions, but they're doing that at the same rate that the ions are coming back together to be molecules. And so you reach a steady state and you have an equilibrium, which in this case is called, or an acid dissociation constant, to show how much the acid dissociates into ions. And in this case, for acetic acid, the acid dissociation constant expression would be the concentration of hydrogen ion times the concentration of acetate ion over the concentration of the acetic acid molecule that stays together. And for this one, the acid dissociation constant would look very similar. I don't need any exponents here because there's no non-1 coefficients. And so we just have the hydrogen ion concentration times the fluoride ion concentration over the concentration of hydrogen fluoride molecule that stays together. Well, we've just learned how to write these equilibrium constant expressions. Basically, you're writing an equation for how do I solve for the equilibrium constant. And so if you knew all the values of these concentrations, or you could solve for the equilibrium constant. If you knew the value of the equilibrium constant and 2 out of these 3, you could solve for the third. So you will see some textbooks and references that do a lot of those calculations. Instead of doing that, I wanted to just make sure that everybody had a big picture understanding of what's going on here. If you had a lot of products and not too many reactants, the products, remember, are in the numerator, so you would have a large number in your numerator and a small number in your denominator. That would result in a large number. So if you have a large value for your equilibrium constant, that means the amount of products is large and the amount of reactants is small. If instead the amount of products is small, you have a small number in your numerator, and the amount of reactants is large, that gives you a large denominator, then the equilibrium constant would be a small value, because a small number over a large number gives a small number. So if your KEQ is very small, you are mostly reactants. If your KEQ is large, you're mostly products. So we have a few examples to apply this. Here we have an equilibrium constant, which we can tell by the power of 10 is an extremely small number. Here we go, 0.000000002. That is very small. So this is definitely mostly reactants. Here we have a number that is extremely, extremely large. And so we know that this equilibrium is mostly product. Here's another case, barium sulfate, that we looked at before, the solubility product constant, and it's not very soluble. This is a very small number. It's mostly reactant, which is mostly undissolved solid. And we have looked at this before. Barium sulfate, according to our solubility chart from chapter 7, is a fairly insoluble compound. So this is mostly stays as undissolved solid. Here we have another small number. So we have something that is mostly the reactant, mostly the acetic acid molecule, and we've talked about this before as well in the previous chapter, that weak acids are weak electrolytes because they mostly stay together as the molecule. Very little of it becomes the ions. So there's very little ion here, mostly neutral, uncharged molecules.